Hi, this is Marwa and this is our sixth video about polynomial functions. As we promised before, we will discuss the fundamental theorem of algebra. In this video, we will understand what it means. We will see how it works with quadratic functions, then cubic, then quartic of the fourth degree, and quintic, which is of the fifth degree. By the end of the video, you will be able to work with any polynomial function you get and find all its roots or zeros. So let's begin. Now, if we look at what we have here, the fundamental theorem of algebra, what does that mean? Actually, it's a simple theorem. Regardless a lot of details, I will spare you the details and tell you that it only means that the number of roots of any polynomial function is equal to its degree. What do I mean by that? Like if we look at this function we have here, this is a quadratic function of the second degree. If it's of the second degree, then it has two roots or two zeros. And we know that roots and zeros are the same thing. If it's of the third degree, it has three zeros. If it's of the fifth degree, it has five zeros. Okay? But those zeros are not necessarily real numbers. They could be real numbers, which includes rational and irrational, and we discussed that in the previous video of the rational roots, so you can look back at it. It could be complex numbers, which is imaginary. It could have a multiplicity. We will see different cases where that apply, but by all means, the number of zeros or roots of a function is equal to its degree, okay? Now, before we start solving equations, I just want you to look at these three quadratic equations we have here, and we start with quadratics because they are the simplest. Before I look at the graph, I will try to find the roots by factoring. Now, if we use factoring here, this function is going to be factored into two linear factors. Now I have x and x, and we know that this is difference between two squares, so that's plus 2 and minus 2, and I can tell that the roots are, or the zeros are, x equal negative 2 and x equal 2. Let's check on the graph here. Yep, we have x equal 2 and x equal negative 2. So we found two real zeros. Now, what about this one? If I factor, regardless the graph, now this is x and this is x, I need two numbers that have the product of 1, which is specifically 1 and 1, positive or negative, depending on the sum. If the sum is negative 2, then that means both of them are negative. So in this case, x is equal to 1, and here x is also equal to 1. Well, this is one root. However, it happened twice, as we discussed before in our zeros. This is polynomial functions video that we have done before about zeros and multiplicity. I believe it's number 3. We can see that the zero here is 1 and it has a multiplicity of 2. So the zero is 1, x is equal to 1, and it happened twice. And this is why, as we discussed multiplicity before, when the graph came at x equal to 1, it did not cross the x-axis. No, it went back up, because here it has a multiplicity of 2, or an even multiplicity. If we look at our last equation, we will see that it cannot be factored. So for you to solve it, you will be using the quadratic formula, which is x equal negative b, positive or negative, square root of b squared minus 4ac over 2a. Now we can see here that a is equal to 1, b is equal to 2, and c is equal to 2. A is the coefficient of x squared, b is the coefficient of x, and c is the constant. When you substitute, I will spare you the details because we have a lot to go through, you will find that your solution is going to be negative 1, positive, and negative I. So there are two solutions. One of them is x equal negative 1 plus I, and the second one is x equal negative 1 minus I. So these are two complex roots. So all three equations are quadratics of the second degree. First one gave you two real roots. Second one give you a real root with a multiplicity of 2. So although it's only one root, but it happened twice, so that counts as 2 roots. And the third one gave you 2 complex roots. One of them, one complex, and of course it's conjugate, like we have discussed in the conjugate theorem, conjugate root theorem. So by all means, in all 3 cases, we have found 2 roots because the degree of the function is 2. Because this function is with second degree, it has 2 roots. This function of the second degree, it has 2 roots. And this is what the fundamental theorem of algebra is all about. Number of roots is equal to the degree of the function. Now let's take a look at, if we have more complicated questions, how do we solve that? We will start with a cubic function to the power of 3, which should be easier than others. Now this cubic function here, we have x to the power of 3 plus x squared plus 4x plus 4. We should first of all look for a common factor whenever we try to solve anything. Unfortunately, we don't have any. So what do I do next? Next step, you should use the rational root theorem, and we have discussed it in a previous video. And this states that any rational root, any possible rational root in this case, is going to be a factor, has to be the quotient of a factor of the constant over a factor of the leading coefficient. Now thank God the leading coefficient is 1, so we can only look for factors of the constant. The constant here is 4. 4 has how many factors? I can make a table. This is x and y. It has 1, -1, 2, -2. Try to extend the table a little. And 4 and -4. These are all factors of 4. What you're going to do simply is that you're going to start substituting for x for each of those values and see what you get. When you substitute for 1, you will get a value. You will not get 0. If you don't get 0, then this is not a root of the function. So 1 doesn't count. When you substitute for -1, you will get 0. How do you substitute? Get back to the rational root theorem video and you will find out. So -1 is a 0. Once I find the 0, I stop. I found one of my zeros. I'm looking for the zeros. What are they? All the roots. I found one of my zeros, which is -1. This is the first one. So I'm going to use synthetic division. Why am I doing this? We use synthetic division to reduce the degree of the function. I started with a cubic function. I need to reduce it to be able to find all the possible zeros. So I'll take the coefficients, 1, 1, 4, and 4. Use synthetic division. This is going to be -1. You multiply, you get a 0. You add, you get 4, -4, then 0. This is remainder, constant, x and x squared. So after I divided, the quotient is x squared, and there is no x term, plus 4. This is what I have left, and that should be equal to 0. Then I can actually factor this, or I can just solve it simply by saying that x squared is equal to -4, which means that x is equal to square root of -4. Now, of course, this is going to be a complex number, which is, we will do some details in case you don't know how to solve this. You have square root of 4 multiplied by square root of -1. And this is, of course, positive and negative. There are always positive and negative are both solutions. So I have positive and negative. Square root of 4 is 2, right? And square root of -1 is I. So the zeros that I found for this equation are -1, 2i, and -2i. So in the first example, we were able to find the roots of any quadratic function. In this example, we had a cubic function. We found one rational root and 2 imaginary roots, and of course they are conjugates, or complex roots. And now we will look at a 4th degree equation. Again, look for a common factor. You couldn't find any, you will go straight to the rational root theorem. Thank God we have 1 as a leading coefficient, so we can check the constant. Same way we did in the last example. I have x and y, and the roots of 12 are positive -1, so I have 1 and -1, positive -2, we have positive and negative 3. This is going to be long. We have positive and negative 4. And we have positive and negative 6. And finally, positive and negative 12. Let's just pray that we get a root soon enough. We will start checking each one of those by substituting for x. Once we get a 0, we will stop immediately. When you substitute for 1, your answer will not be 0. When you substitute for negative 1, your answer will not be 0. When you substitute for 2, you will get a 0. So this is one of the zeros. So again, I'm looking for my zeros, and I found the first one, which is 2. Next step, as we did last time, synthetic division. You have 1, negative 4, 1, 12, this is positive, sorry, and negative 12. Bring down 1, multiply, you get 2, negative 2, multiply, we got negative 4, that's a negative 3, multiply, you get a negative 6, add, you get a 6, multiply, you get a 12, add, you get a 0. So we have reduced it from the 4th degree to a cubic. This is our remainder constant x, x squared, and x cubed. So we have x cubed, our quotient is x cubed minus 2x squared minus 3x plus 6 equal to 0. Now, can I solve this in any way? Let's think about it. Is there a common factor? Is there anything I can do? Unfortunately not. So what do we do? Again, rational root theorem. So what are the rational roots in this case? I am going to use the same table I have, but I just need a smaller eraser. Of course, 12 is not a factor. 6 is a factor. 4 is not. 3 and 2 are factors, and 1 are factors. So factors of 6 are 1, negative 1, 2, negative 2, 3, negative 3, and 6, negative 6. And I'm going to start all over again. This is your workout. You don't even, like, just to save space, I erased it to do the new question. And when I check again, when you substitute for 1, you will not get 0. When I substitute for negative 1, I will not get 0. When I substitute for 2, actually I will get a 0. Okay, so this is my second 0. So what happened here? What happened is that 2 as a 0 was repeated. So the 0, x equal to 2, has a multiplicity of 2. Again, I am going to use synthetic division. However, when you use synthetic division this time, you don't use the original equation. You use what you got, the quotient after dividing by the first 0. Our goal is to reduce this power until we get to a quadratic to be able to find all zeros we have. So I'm going to have 1, coefficients are 1, negative 1, negative 3, and 6. Synthetic division again, I have 1 here, 2, 0, 0, negative 3, negative 6, and 0. Again, remainder, constant, x, x squared. We are left with x squared minus 3 equal to 0. If I try to factor it, sorry, the lines are not straight. We have x squared minus 3 equal to 0, which makes x squared equal to 3. Then x equal, when you find the square roots, positive and negative radical 3. I got an irrational 0, and of course with its conjugate. So I have radical 3 and negative radical 3. Another way to write this with, it will be 2 multiplicity of 2 and positive negative radical 3. These are the zeros of this function. So we have been through a quadratic, a cubic, and a quartic. Now let's look at this case. Here I have to the power of 5. First thing I'm going to do, as we said, check for a common factor. We do have a common factor. I can take x, I can factor out x from all these terms. When I do that, I'm going to have x multiplied by x to the power of 4 plus 3x squared minus 4, and that's equal to 0. Before I go any further, find your first 0. Here I have x equal to 0. So when I look for my zeros, the first one I found is 0. Thank God. What I have first is a 4th degree trinomial. Now, the quartic trinomial that looks like that is a special case. Why is the special case? Now, let's just remember what we know about quadratics. If this was a quadratic equation, just think of it that way. It would have been x squared plus 3x minus 4, right? If it was a quadratic, and you would have factored it, saying that I have x here and x here, and if the product is negative 4, then 4 and 1 would work, and I have a sum of positive 3. This is negative, so I know both are different signs. They have to be of opposite signs, or else how would you give you negative when you multiply them? The positive number has to be 4, and this has to be 1, so you could get a sum of positive 3. This is in case it was a quadratic. Why am I saying that this is a lot similar to this? Now, if you look at the quadratic here, the degree of the first term is 2. The degree of the second term is 1. So this is double this. Again, the same here. The degree is 4, and the degree of the second term is 2. This is double of this degree, and I have a constant in both cases. So I can just pretend that this is a quadratic. I'm gonna erase this power and put the fourth power that I have. Just bear with me, I'll get to the bottom of this in a minute, okay? And in this case, both of these will be squared. Now I'll check before I go further by multiplying x to the power of 2 multiplied by x to the power of 2. This is x to the power of 4. 4x squared minus, let's write it in details. I have 4x squared minus x squared, and 4 times negative 1 is negative 4. So this is x to the power of 4 plus 3x squared minus 4. Isn't this the same as this? Yes. So I can actually factor it. And actually this is a kind of special case that you get to see a lot. It's a quartic trinomial. It's of the 4th degree, but yet it's a trinomial. Its middle term is squared, and the last term is a constant. You can pretend it's a quadratic and just factor it, which we're going to do here. Sorry. So if I pretend it's a quadratic and factor it, I'll get x squared, as we said a minute ago, plus 4, and x squared minus 1. Then I'll solve it normally, saying that x squared plus 4 is equal to 0. That makes x squared equal negative 4. We did this before. We'll take the square roots of both sides. You have x equal positive and negative 2i, because of course the square root of a negative number has to give you an imaginary. And on the other side, I have x squared minus 1 equals 0. That makes x squared equal to 1, which makes x equal to positive and negative 1. So the zeros are 0, 1, negative 1, 2i, and negative 2i. Of course, these are not in order. So let's look back at what we did here. We did factor when we could factor out a common factor in this case. Then we got a quartic trinomial that we factored, again, same way we do with quadratics, and we found all zeros. Now, I want you to take in consideration that this was to the power of 5, and it had 5 roots. 3 real numbers and 2 complex. So to the power of 5, it had 5 roots. The question before that was to the power of 4, and it had 4 roots. 2, all of them are real numbers, 2 of them are rational, and the other 2 are irrational, and of course they are conjugates. First question, when it was to the power of 3, it had 3 roots, 1 rational and 2 complex, and both of them are conjugates, like the conjugate theorem states. So this is the fundamental theorem of algebra, which states that the number of roots or zeros for any polynomial function is equal to its degree, exactly the same as the degree of the function. That includes real roots, complex roots, and multiplicities or multiple of roots, like we had in the second case here, where 2 had a multiplicity of 2. It happened twice, so we counted 2 times. I hope this have been helpful for you, and you are able now to understand better how to work with rational roots and find complex roots of any polynomial function. Look for a common factor first. Can't find any, or even if you find any, try to search for a rational root. Once you find that, use synthetic division. Only in a special case of a quartic trinomial that looks like a quadratic, you can factor it immediately. And even if you don't get that, if you use rational roots, you will be able to find 1 and -1 with synthetic division. You will get to the bottom of this. I'm just showing you a shortcut for this question. I hope this has been helpful, and if you need any more basic stuff about this concept, go back to the previous videos about polynomial functions, and thank you so much for watching.